Hi, today I'm going to be talking about Microvium. It's a JavaScript engine I wrote for microcontrollers. The intended audience for this presentation are people with some familiarity with ECMAScript and have some interest in compilers and interpreters. This video is not a tutorial. It's not aimed at users of Microvium primarily. First, a little bit about me. I'm a full-stack developer and I'm also a firmware engineer. When I'm working on the full-stack side, I generally program in JavaScript or TypeScript. And when I'm on the firmware, I generally program in C or C++. I like JavaScript and I like firmware development, but the issue is size. A desktop class machine might have around 16 gigabytes of RAM, while an embedded firmware device might have only 16 kilobytes of RAM. That's 1,000,000 times smaller. Here are two examples. These are two of the biggest microcontrollers I've worked on in my career, although you can get much bigger than this. On the left, we have a device with 256 kilobytes of flash and 8 kilobytes of RAM. On the right, it's the same amount of flash, but a little bit more RAM. These devices are pretty middle of the range microcontrollers. The last time I checked, around half of the microcontrollers selling on DigiKey were actually smaller than these. So I needed to add some scripting capabilities on these projects. This was some years ago. And I wanted to use JavaScript in part because I think it's a great universal language and it's already a language used in so many places. And also because you can write shared business logic that would easily run on the backend servers or web interfaces for these projects. I'll add that on these projects, there was already some C firmware running, which I didn't want to get rid of, and it's already taking up most of the space. So the question is, if I want to also run JavaScript on these devices, what are my options? I won't beat around the bush. There are not a lot of JavaScript engines that fit in this tiny space. JavaScript engines come in a wide variety of sizes. On the larger end of the spectrum, we have big jittered engines like V8 and SpiderMonkey. Let me hide my camera here. If you go to smaller engines that are designed for resource-constrained environments like XS, QuickJS, or Espruino, these are in just the hundreds of kilobytes, which are significantly smaller. If you're willing to give up some language features, there are engines like V7 and its successor MJS, which compile to just tens of kilobytes. MJS in particular is around 50 kilobytes. If you're trying to fit on a device with, say, 256K of flash, MJS fits, but it's quite a significant size cost. Note that the shapes on this slide are roughly to scale. At this size, you're now losing a lot of the JavaScript language. You lose a lot of the standard library and built-ins. You lose closures. You lose exceptions and try-catch. You lose proper ES module support, although MJS does have another module system, among other things. But you can go even smaller than this. There's an engine called Elk that's around 11.5 kilobytes of flash by my measurements. Elk is the smallest JavaScript engine I've come across so far in the wild, so it's really at the bottom end of the size spectrum. Elk forgoes the same features as MJS, but additionally we lose var and const. That is, only let bindings are supported. We lose do and for, that is, only while loops are supported. We lose switch statements, we lose computed member access, among other things. Even at this small size, Elk still has a parser, so at runtime it's consuming actual source text. That makes up a significant portion of the size of the engine, and that's one of the places Microvium makes different trade-offs. So where does Microvium fall into the spectrum? Microvium is roughly the same size as Elk, compiling to just 12 kilobytes at the moment, subject to compiler settings and platform, but the size will grow a bit as I develop it further. It forgoes having a parser at runtime, and in return it gets back a number of really useful features. You get back basic variables, control flow statements, and all of that. You get try, catch, throw. You get closures, function expressions, arrow functions, basic support for classes, basic support for ES modules, and most recently I've added support for async await. There's other nice to have features like template strings and things like that. There's still lots it doesn't support. To list a few, there's pretty much no standard library support. That is almost no built-in functions and objects. And there's no support for variadic functions. Properties don't have attributes. There's no symbols or big ints. So there's still lots that it doesn't have. So what is Microvium? Microvium is a tiny JavaScript engine for a small but useful subset of the language. It's MIT licensed, completely open source, both the compiler and runtime engine. It's optimized for microcontrollers, but the implementation is just portable C code, so you can use it basically anywhere. Because it supports a subset of the ECMAScript standard, you can write code that has the same behavior when running on Microvium as when running on a desktop class JavaScript engine. But you're not going to be running arbitrary code off NPM on Microvium. One of the things that makes Microvium compact, and quite unusual even among the smaller JavaScript engines, is that it uses a 16-bit slot size. That means that variables, array elements, and property values are 16 bits each. The 16-bit slot uses a tagged pointer encoding with a 1 or 2-bit tag, and the tag discriminates between one of a number of possible values. It can hold a 14-bit integer. It can hold some basic values like true, false, nan, etc. Or for most other things, it can be interpreted as a 16-bit pointer to the garbage collected heap. Because pointers are 16-bit, it does mean that the heap is limited to 64 kilobytes. I'll reiterate that it will run fine on a 32-bit device or larger. It just won't be able to make use of the full address space. It can also point back into the bytecode image, which would generally be stored in Flash, so it's less costly than heap memory and RAM. There are a few language features of ECMAScript that are not supported by Microvium. Some of these are just because I'm one guy and I have limited capacity to add these features. But the more interesting cases are features that I've chosen to omit because of the tiny constraints, the tiny size constraints. For example, properties in Microvium do not have attributes, that is writable, enumerable, or configurable. So while you can use something like reflect.ownKeys in Microvium to enumerate all the properties of an object, you can't use, say, object.keys. The difference between these two functions is that the latter returns enumerable property keys, but Microvium doesn't record property attributes, so it doesn't know which properties are enumerable and which are not, and so this function is just not supported. And this is a general pattern I've taken in Microvium. If a feature exists in the engine, I've tried to stick as closely to the standard as possible. Otherwise, I've either omitted it or it's an error. I'm sure there are edge cases where this doesn't hold true, but I've tried to follow this principle. So another example is you can't use a for in loop in Microvium because, again, it doesn't know which properties are enumerable. And there is no delete operator because you don't know which properties are configurable. The limitations that Microvium puts on properties allows it to represent objects very compactly in memory. If we have a simple object with two properties, such as here with x and y, the memory structure looks roughly like this. So let me get out my laser pointer to explain this one. In the diagram, each rectangle is a slot, which is 2 bytes. All allocations in Microvium in the garbage collected heap have a 2-byte allocation header. That's this header here. There are also properties. This is the X property and this is the Y property, which consists of a 2-byte property key, in this case the string X, and then a 2-byte value, in this case the value 1, which may point to larger structures if it doesn't fit in that 2 bytes. So each property here is 4 bytes. There's also a next pointer and a prototype pointer. I won't go into detail about these now. Another language limitation is that Microvium functions are not full objects. If you use, say, type of on a function, it tells you that it's a function, as you would expect. That works fine. But if you try to access properties on the function, this is treated as an error. Similarly, you can't enumerate the keys of a function. It's also an error. And you can't use new on an arbitrary function, in part because otherwise you would be able to observe the absence of the prototype property. The caveat to this is that classes declared with ES6 class syntax are both functions and objects, so you can set properties on them. Doing so makes classes more expensive, but as a user, you only pay for that overhead when you explicitly declare a class. But neither objects nor classes in Microvium are the most efficient way to store state. Closures are significantly more efficient, so let's talk about those. So here we have a simple closure example. The function inCounter closes over the variable x in its parent function, and the variable myCounter references that closure. In memory, the myCounter variable is a 2-byte slot that references the closure on the garbage collected heap. The closure contains a function pointer that points to where in the bytecode it should run when the closure is called, and the bytecode itself is stored in ROM. And it contains the variable x, which is another 2-byte slot. And because this is a heap allocation, there's an additional 2 bytes for the allocation header. So this closure in total takes 6 bytes of heap memory. There's also the makeCounter variable here, the makeCounter function itself, which points directly to the bytecode, which is typically stored in ROM or flash, so it doesn't incur any RAM overhead. So this example takes 10 bytes in total. Clearly this wouldn't be possible if functions had properties and those properties had attributes, etc. A recently introduced feature in Microvium is async await. Microvium takes a novel approach to async await. If you have an async function, such as foo here, and that calls another async function, such as bar, internally, the continuation of foo is passed as a callback to bar in a special purpose register. When bar terminates, it will call the continuation via the job queue, of course. It will be called with 2 arguments. The isSuccess argument saying whether bar resolved or rejected, essentially, and then the result or the error in the case of a failure. So in cases like this one, there are no actual promises instantiated. This is allowed because the promise in this example is not observable to the user code. Microvium recognizes the syntactic form of a function call immediately followed by an await, and will pass the caller's continuation to the callee in this case. I call this syntactic form an await call because it's call immediately followed by an await. On the other side, the async function recognizes that a continuation is passed, so it doesn't construct a promise. A suspended async function, such as in the case of foo, is represented in memory as a single allocation. Allocations in Microvium have a 2-byte header, among other things. This marks the value as callable so that it can be directly used as a callback without any other ceremony. And this happens to share the same type code as closures. So these async function continuations are treated as closures. Continuations have a resume pointer, which points to the bytecode address at which to resume, which would be in the middle of the suspended function. And they have a callback pointer, which points to the caller's continuation. That's 3 slots, which in Microvium is 6 bytes. As a point of comparison, I did a measurement of the size of a suspended async function in Node.js on my desktop machine, which is not a fair comparison, but it's an interesting one. And it measures to be about 420 bytes for this same example. This is 6 bytes for the core state that the engine uses, but of course additional state may be required depending on the user's actual code. For example, it'd be additional slots for any variables. Depending on where the await point is in the function, there may be additional temporaries to store the stack machine state at the await point. If the async function is nested in another function and accesses its variables, there will also be a pointer to the outer scope. So the size of a continuation depends on static analysis to determine what state the user code requires to be preserved over all the await points. The same continuation is reused for each await point in the function by just modifying its bytecode pointer at each await point to the corresponding resume point. Since the continuation houses the state of the async function over its lifetime, you can think of the continuation as a kind of heap allocated stack frame in a sense. It's storing roughly the same information. If the async function wasn't await called, that is, if the resulting promise wasn't immediately awaited, the engine would also construct a promise. A promise is a 10-byte structure with all the normal object machinery and an internal status slot to say if the promise is pending, resolved, or rejected, and a callback slot that points to any of the awaitor's continuations. When the async function terminates, it will just invoke any of the awaitors via the job queue. So the async function, from the async function's perspective, the promise is just an indirect way of keeping track of awaitors. I see this as kind of a pay-as-you-go design of async await. The fixed overhead is just 6 bytes, and then additional space is used depending on what the user code needs. In any case, Microvium's implementation of async await is at least an order of magnitude smaller than most, if not all, other JavaScript engines, making it feasible to use the feature on devices with only a few kilobytes of RAM. You might be interested to know a little bit about the Microvium heap. So here are some quick-fire facts. Microvium uses a compacting garbage collector. The fact that it's compacting means that no bytes are wasted to fragmentation. It's designed to minimize idle memory usage so that the most memory is available to the host at any time. It does this by releasing any free space back to the host after doing a garbage collection. The assumption is that Microvium is part of a larger host firmware, and when Microvium isn't doing work, you want its free memory to be available to the host. As you know, an allocation header is 2 bytes. This includes a 4-bit typecode and a 12-bit size. So objects and arrays in Microvium are limited to 4 kilobytes each. Another interesting thing about the garbage collector is that it actually compacts arrays and objects. Arrays in Microvium grow their underlying capacity geometrically, and a garbage collection cycle truncates the unused capacity. Normal objects in Microvium grow actually as a linked list for the reason of fast insertion time, and then a garbage collection cycle will compact it into a contiguous block to only use 4 bytes per property. Microvium has support for snapshotting. Not only does it support it, but it relies on it as a foundational part of how you use the engine. You start by running the application on your local machine or build server. When the application has finished running, that is, when all the top-level code has executed and reached its terminal state, Microvium captures the state of the app to a file, including the state of all the variables and objects. Microvium is implemented as a virtual machine, of course. So the snapshotting process is roughly the process of capturing the state of all the memory of the virtual machine. The snapshot file is then what you deploy to the target microcontroller. Once it's on the device, you can then resume execution. Or more accurately, the app can't resume as such because it's already run to completion before the snapshot was taken. But the firmware can now call functions in the snapshot. From the perspective of the app, it went to sleep on one machine and woke up on another machine with a potentially different host API and different engine capabilities. When running on the desktop machine, it has access to a parser and the ability to import modules, as well as potentially other capabilities of that host machine. This is what we might call compile time, because it's the phase of your pipeline that happens before you deploy. And the result of this phase is a deployable binary, which is the snapshot image. And in this way, it echoes the process of compilation. When running on the target microcontroller, the application might have access to things like GPIO and other APIs that your firmware wants to expose. I say might have because by default, Microvium doesn't give you any runtime I/O. It's completely sandboxed and up to you what you want to expose. So what I mean when I say Microvium doesn't have a parser is that the runtime engine doesn't have a parser, but the compile time engine has a parser. You just lose that capability when you transition to runtime. Here's a quick example to illustrate some of these concepts. Here I have a new folder with a single JavaScript file called script.js, which will be our guest JavaScript. I'm writing a simple hello world script to get started. This console.log statement is at the top level, so it will execute at compile time. We can then compile this in a terminal by running the command microvium script.js. This command is similar in principle to running Node.js on a script, except of course it's not Node. And like a Node app, the script is able to perform I/O. Here it's outputting to the terminal. Unlike running a Node.js application, we get a binary output file as a result. This is the snapshot of the virtual machine in its terminal state. This is the file that we would want to download to the target device. Like I noted earlier, this process echoes a traditional compiler in that it takes source text as input and produces a single binary output. The script doesn't yet do anything at runtime. By the time the snapshot is taken, the console log statement has already executed. So how do we implement some runtime behavior? The way that works in Microvium is that the application at runtime doesn't do anything unless the host firmware calls it. Functions in the snapshot can be identified to the host by a numeric ID. Here I'll use the ID 42. To make the JavaScript function available to the host, we use a built-in function called VM export, giving it the ID and the function to export, which here I'll just use an arrow function. Like all top-level code, this whole statement is executed at compile time, telling the host at compile time that this function is available at this ID. This function is now available for the compile time host to call if it wants to, but the more important thing is that these IDs are sticky. They travel with the snapshot so that the runtime host can look up this function and call it. This print function doesn't exist yet, so we'll have to add it. Like I said earlier, Microvium doesn't give any out-of-the-box support for I/O at runtime. But like we can export a function from the VM, we can also import. Here I'm assuming that the print function will be available at ID 12, just a made-up number. When the snapshot is restored at runtime, the host must provide all the resolutions for all these IDs. So then what would happen if we called console.log at runtime? The built-in console.log becomes something like a detached proxy in the snapshot, because it's not associated with a persistent identifier. If you called it, it would just be an error. But as a user, you're free to overwrite the log property of a console object if you wanted to make it persistent across the snapshot, like the print function here. To actually run this, we need a host. Well, I could show you a C++ or C host. For the sake of time, it will be faster for me to actually show you a JavaScript host, and we'll run it on Node.js. And this will still demonstrate many of the same basic principles. We can do this because I recently created a WASM build of Microvium and deployed it as an npm package. So let's create a new JavaScript file for the host. We'll be running this file in Node.js, not Microvium. The first thing we'll need to do is bring in the snapshot, which we can load as we normally would load a file in Node. If you recall, this was saved as script.mvmbc. To restore a snapshot, we'll need to run a Microvium instance in Node.js, which we can do with the WASM library. So we'll need to install the WASM library. And while that's installing, let's continue. We'll need to restore the suspended states of the virtual machine. To do this, we provide the snapshot as well as the set of imports that the virtual machine needs. If you recall, the VM imported a function, the print function, at ID 12. So let's just implement this by logging to the console. Now that the VM is loaded, we can access its exports. If you recall, the guest script exported a function with ID 42. Let's bind this to the name say hello. Now we call the function running inside the Microvium virtual machine. So now we can run this script. This is the host, so we're just running it with Node. And there we go. It runs the guest function. So to recap, we're running a Node.js program, which in turn runs an instance of the Microvium virtual machine using a WASM build of the Microvium runtime engine. The WASM library could be used in the browser if we wanted to. The guest at compile time tells its compile time host what functions it wants to import, and then at runtime these are resolved against the new host. And similarly for the exports, which are implanted in an export table during the compile time run, and then resolved against the export table at runtime. The say hello value here in the host is a function proxy of the corresponding guest function. In general, there's something like a membrane between the two engines that allows values to be passed between them. So what benefits do we get from using this snapshotting approach? An obvious benefit is that startup time at runtime is quick. By the time the application has been snapshotted, all of the module loading, initialization, and potentially dependency injection can already have been completed, so that none of that needs to happen at runtime. To restore a snapshot at runtime can take just a fraction of a millisecond. Related to the quick startup time is that if you have any lookup tables that are expensive to compute, you can easily pre-compute them at compile time to improve runtime performance. Microvium runs a garbage collection cycle before taking the snapshot, and any compile time code that is no longer reachable will be collected at this time and not contribute to the size of the snapshot image. The snapshotting approach allows Microvium to implement support for import and export with zero runtime overhead. The runtime engine doesn't need to know at all about modules, since it only deals with the program after all the top-level code has finished executing, including transitively executing the whole module graph. In this sense, Microvium takes the role of a bundler as well, because it takes as input a set of distinct source files, but produces one deployment artifact, which is the snapshot image. But unlike a typical bundler, it does so in a way that doesn't require any configuration files, like a webpack.config. So that's Microvium. I've talked about why I created it and the niche it fits into. I've discussed some of the design decisions that lead to Microvium being really small. I've talked about snapshotting, how it takes the role of a compiler or of a bundler, but with less ceremony, and how from the app's perspective it's just moving from one host to a different host with different capabilities. And I've covered a basic code example to illustrate some of the concepts. I hope you found that interesting. I'll see you again next time.